Hello everyone, I am Li Qina from the Electronics and Information Engineering Teaching and Research section at Wuzhou University and welcome you to this mini lecture. Today we'll study the second part of Chapter 6, Complex Frequency Domain Analysis of Discrete Time Signals. In previous chapters, we have learned about the discrete time Fourier transform, DTFT, which provides a way to represent discrete time signals and systems in the frequency domain. However, some sequences do not satisfy the conditions for the DTFT to exist, meaning their discrete time Fourier transform does not exist. As a result, we cannot represent these sequences in the frequency domain. To address this issue, this section introduces a method for analyzing signals in the complex frequency domain, namely the Z-transform. Today, we will focus on section 6.4, Z-transform of discrete time signals and its properties. Next, we will approach this lesson through the following topics. First, let us discuss the definition of the Z-transform. The Z-transform is a mathematical transformation applied to discrete time sequences and is commonly used to solve linear time invariant (LTI) difference equations. It converts a discrete time sequence into an expression in the complex frequency domain, allowing difference equations to be transformed into algebraic equations. Its role in discrete time signal processing is analogous to the role of the Laplace transform in continuous time signal processing. The Z-transform is an important tool for analyzing problems in linear time invariant discrete time systems. The Z-transform of a sequence Fk is defined as follows, where Z is a complex variable, and the complex plane on which Z lies is called the Z-plane. In the definition, if the summation is taken over K from minus infinity to plus infinity, it is called the two-sided Z-transform, defined as follows. If the summation is taken over K from 0 to plus infinity, it is called the one-sided Z-transform, defined as follows. In this lesson, we will primarily focus on the one-sided Z-transform. For any given sequence Fk, the set of all values of Z for which the Z-transform converges is called the region of convergence of Fz, denoted as ROC. As shown in the formula, the Z-transform exists if a series is absolutely summable, and the corresponding set of Z values for which the series converges is the ROC. For a Z-transform, both its pole zero function and the ROC determine the original sequence. Next, we illustrate the ROC of different types of sequences through some simple examples. Example 1. Find the one-sided Z-transform and ROC of a real exponential sequence Fk equals a to the k times uk. First, substitute the sequence into the definition of the one-sided Z-transform. After simplification, Fz becomes the sum of an infinite geometric series with common ratio q equals a times z to the minus 1. The series converges when the absolute value of z is greater than the absolute value of a, so the one-sided Z-transform exists. Using the formula for the sum of a geometric series, we can obtain the one-sided Z-transform of a sequence. The ROC can be represented in the Z-plane, where the horizontal axis is the real part of Z and the vertical axis is the imaginary part of Z, as shown in the right figure. The ROC is the region outside the circle with the pole at Z equals a as the boundary. Example 2. Find the one-sided Z-transform and ROC of the rectangular sequence Rnk, where n is the length of the rectangular sequence, also called the window width. This sequence is therefore a finite-length causal sequence. First, substitute the rectangular sequence into the definition of a one-sided Z-transform. After simplification, Fz becomes the sum of a finite geometric series with common ratio z to the minus 1. The series converges as long as the absolute value of z is greater than 0. In general, if Fk is a finite-length sequence, Fz is absolutely summable as long as each term Fk times z to the minus k is bounded. Since Fk is bounded, the convergence only requires that each z to the minus k is bounded. Therefore, the ROC of a finite-length sequence is generally the absolute value of z greater than 0 and less than infinity, and it may sometimes include the points z equals 0 or z equals infinity. The Fourier transform and the Z-transform are both important tools in signal processing, and there is a close relationship between them. By comparing the definitions of the Fourier transform and the Z-transform for a sequence, we can easily derive the relationship between them, as shown in the following equation. Here, Z equals e to the power of j omega represents a circle of radius r equals 1 in the Z-plane, which is called the unit circle. This equation shows that the Z-transform evaluated on the unit circle is exactly the Fourier transform of the sequence. If the Z-transform of a sequence is known, the Fourier transform can be easily obtained using this equation, provided that the ROC includes the unit circle. Please consider, if the ROC of the Z-transform does not include the unit circle, does the Fourier transform of a sequence exist? When a sequence undergoes operations in the time domain, such as addition, shifting, or multiplication, its Z-transform exhibits corresponding operations. These relationships are referred to as the properties of the Z-transform. Next, we introduce some important Z-transform properties. Linearity. If a new sequence is formed by a linear combination of two sequences in the time domain, its Z-transform is the same linear combination of the Z-transforms of the individual sequences. The ROC of a new sequence is the intersection of the ROCs of the original sequences. If there is no overlapping ROC, the Z-transform does not exist. In some cases, however, the ROC may expand. Time shifting. If a sequence is delayed by n samples, its Z-transform is the original Z-transform multiplied by z to the minus n. Convolution. If two sequences are convolved in the time domain, the Z-transform of their convolution equals the product of the individual Z-transforms. The ROC of the convolution is the intersection of the ROCs of the original sequences. Similarly, if there is no common ROC, the Z-transform does not exist. Other important properties of the Z-transform exist as well. You are encouraged to derive and study these on your own. Please reflect on today's lecture and complete the following homework exercises to consolidate the concepts learned and deepen your understanding. That concludes today's mini lecture. See you next time.